All right, last class, and it's snowing. DJ drop tables, thank you. So I noticed you don't have your deck today. What happened?
Remember how I forgot to get my girlfriend a gift?
Yes. You had to buy her a gift now?
Yeah, but I didn't have any money.
Yeah, so what'd you do?
I had to flip my board.
You sold your deck?
Yeah. But
how are you gonna drop the beats now?
I gotta make some bread until I can make to get a new one.
But this is gonna interfere with your album now, right?
Yeah, it's probably delaying it back, like, you know.
I mean, how long? You don't have anything.
It's pretty rough out here, yeah.
All right. Well, he's got his problems. We have database problems, but this is the last class. And as I said, it's just gonna be the final review and then a system potpourri for what you guys voted on for what you wanted to talk about. So just real quickly, the remaining things for the semester, Project 4 is due next week on the 10th. Man, that's way off. When's the 10th? Is that Monday or Wednesday? Not even close, right? So Tuesday, December 10th, both the final project and the extra credit will be due. We promised you feedback. We found people plagiarizing, so we have to deal with that first, and then we'll hopefully be able to put out the reviews for or the feedback for everyone else within like the next day or so. Okay. So I apologize for the delay. Overall, they were pretty good. Some are better than others, obviously, but the feedback will help guide you to finish it up. Yes.
Wait, so they put the extra credit and then plagiarize there?
So you remember how when you filled out the form, you had to click the checkbox. Yes, I agree. I'm not going to plagiarize. They still plagiarize. Yes.
And they'll still get 0.
Well, at the very least 0. Whether I go talk to the provost or not, that's another story. Yeah. They, again, CMU doesn't f around. They take this seriously. And the fact that it made you click that checkbox, and it's on video saying, me saying don't plagiarize, you don't have any evidence. You're not you, but I'm just saying whoever did it. No, yeah. Yeah. And then the final exam is due on Monday, December 9th. Actually, going back to extra credit. This is why we have, it's like a wiki style, so we have revisions. So the person could go back and try to remove the plagiarized text, but it's still in the database. You can always go see it. Anyway, again, not you, but in general. All right, the final exam is on Monday at 5:30 p.m. in Posner Hall, which I think is over there, the old business school. Yeah, so we'll cover that first, okay? So any questions about the extra credit or Project 4? And then for homework 5, we will have that graded and released by Friday, whatever, I think it was due yesterday, so 4 days after that. Unless everyone has already turned it in, we'll send it out, okay? All right, the final exam. All right, so you have to take it, or you don't have to, but you should. This is not live yet, but I'll post this after class. This will be basically a summary of everything that I've talked about. Like it's the same thing I did for the midterm. It's like the sheet of everything you need to know, what chapters in the book, what homeworks matter, and things like that. Again, Posner Hall 100 at 5:30 p.m. Don't come to this room. And then if you're curious why you should take this, other than you want to pass the class, you can watch that video. All right, so what do you need to bring? You should bring your CMU ID because it's a class of 95 people, 96 people. I don't know everyone, so I need to check your ID. Just like the midterm, it's 1 page of handwritten notes, double-sided. No shrinking down the slides, no copying and pasting the text. If you write it by hand on your iPad and want to print that, that's okay. But again, there's no like text, right, from a word processor. And then if you were in the class on Monday, bring your extra credit coupon. And you have to turn that in when you turn in your exam. So the things you get optional, if you want to change your clothes halfway through, somebody did that 2 years ago. I'm fine with that. Because also it's at 5:30, you could bring food. I think we'll give out candy. I'll try to do something better than that, but don't, I can't promise anything. Right? It's not going to be a full 4-course meal before the exam. What not to bring? Again, I think we talked about all the problems on the midterm. Everyone brought weird stuff in previous years. 2 years ago, again, somebody brought their roommate. Just to hang out, don't do that, okay? All right, before we get into the course material for the exam, yeah, sorry, go ahead.
On the final exam schedule, it says it's on Porter 101.
Is that what PH means?
Yeah.
All right, then yeah, whatever that is, yes.
Okay.
Where's Porter Hall? Oh, that's the one over there, yeah. If it's not Gates, I don't know where it is, right? I'll be honest. This is my 7th year. Okay, so, right, so I'll announce this on Piazza as well. I need everyone to fill out the course evaluations. I don't care whether you say I'm an awful person, I have bad hygiene, or you hate the class. That actually is useful to me. I actually read these things. So the things that I'm interested in getting feedback from are like, was there a particular homework assignment you thought was unnecessary or stupid? Anything about the projects? I mean, you've seen my announcement on Piazza that we're looking for people to help with expanding Bus Hub further, fixing all the things that maybe went wrong this semester. But if there's, again, something about the project that you thought was too hard, the pacing was not right, you wanted more documentation, less documentation, you thought it was too easy, too hard, again, that feedback is actually super useful to me, right? So undergrads are awesome at filling out course evaluations. Like if your shit stinks, they'll tell you. The master students, you guys just click 5, 5, 5, 5 on everything. Andy's the greatest professor. I don't want any of that, right? Just like, I actually read this. The university apparently reads it too. I don't care about them, but I actually make the course better based on your feedback, right? One year, a kid psychoanalyzed me with the Myers-Briggs test in the feedback. That was useful. So again, please go fill this out, and I'll send a reminder on Piazza. All right, so I didn't have office hours on Monday, but I'll have extra office hours this Friday at 3:30 in my office, and then I'll have my regular office hours at 1:30 on the day of the exam. If you can't make either of these and you're dying to talk to me, please send me an email, and I'll try to make arrangements. I may have to do it over Skype or Hangouts because of the baby. And then all the TAs will have their regular office hours up until and including December 14th. Right, so the due date for the project 4 is on the 10th, but again, you get 4 late days, so it'll go out into the 14th. Okay? Any questions about office hour stuff? All right, so this always comes up every year. What do you need to know from before the midterm? So the exam is not cumulative, meaning like I'm not going to ask you questions specifically about like buffer pools, right? How does this eviction policy work? But you obviously need to know, it's a part of a database system. We've covered it to the full stack. You need to know how all these different pieces work together. So the things that you have to know about from the previous, prior to the midterm would be the buffer pool management, hash tables, B+ trees, storage models, and then inter-query parallelism, which is, again, running multiple queries at the same time. And you obviously need to know how that works because you have to do transactions that could be updating the database at the same time. Okay? So this is clear. We're not asking you specific questions like in the earlier homeworks before the midterm, but this is background knowledge that you just, if you forgot this already, you have other problems. Okay? All right, so the main thing we spent time talking on was about transactions. Right? You should be aware of what the basic concept of ACID, what are the different properties that are combined in the acronym, and what the data system is supposed to provide. Then we talked about the difference between conflict serializability and view serializability. Remember, view serializability, nobody can actually do, so there's no way to actually check this. It's just a higher level concept. But for conflict serializability, you want to know how to check this and how the data system can ensure that it generates a schedule that's guaranteed to be conflict serializable. What it means to have a recoverable schedule, right? That basically means no cascading aborts. And then isolation levels and the anomalies, right? Dirty reads, unrepeatable reads, and phantoms. Then we talked about concurrency protocols that actually generate schedules on the fly for arbitrary transactions that are conflict serializable. So we spent a whole class talking about two-phase locking. So as you know what the basic protocol is, what the difference between the non-rigorous and rigorous one is. What's the difference? What does rigorous two-phase locking mean? In the back, yes.
You release all the locks at the end.
Thanks, Matt. Yeah, so rigorous is you release all the locks at the end. There is no shrinking phase. Regular two-phase locking, as soon as you release one lock, then you're now in the shrinking phase, and you can't acquire any new locks. Then we talked about multi-granularity locking, right? And the big thing there was the intention locks, right? How do I notify or how do I post information about what I'm going to do at the lower levels of the lock hierarchy in the upper level, so I don't have to take maybe locks on everything. Right? If I have to take a lock on, if I want to update 1 billion tuples, and my table has 1 billion tuples, I better off just taking a single lock on the table rather than locking every single individual tuple. And then it's important to know how you release these locks. Like in what order? Is it top down or bottom up? Then we spent a lecture on talking about timestamp ordering and concurrency control. All right? So you should know what the Thomas Wright rule is, the basic protocol that we talked about. Then we spent time talking about optimistic concurrency control. What are the 3 phases? Read phase, validation phase, and write phase. When do we actually acquire a timestamp for a transaction in these different protocols? In the basic timestamp ordering, when you get a timestamp? When the transaction starts. In optimistic concurrency control, when you get a timestamp?
Very valid.
What's that?
Very valid.
When you validate, yes, when you finish the read phase. Then we talk about multi-version concurrency control. I'm not going to worry so much about the concurrency protocol that you would use in MVCC, like either you're doing MV2PL or MVOCC. I more care about the version storage and the ordering of the delta records, or doing append only, or you're doing the time travel tables, and then how you want to do garbage collection. Then we spend a lot of time talking about crash recovery. Question, yes?
I just wanted you to brief a little bit about the isolation levels.
Right, so the isolation levels, again, it's sort of at the very top you have serializable isolation, and then below that you have repeatable read, below that you have read committed, and below that you have uncommitted read. And so basically, as you go down that hierarchy, the database system is not enforcing or protecting you from certain kind of anomalies. So if you're serializable isolation, then you don't have phantoms, you don't have dirty reads, and you don't have unrepeatable reads. But then if you go down to repeatable read, then you're not going to do phantom checking. If you go down to read committed, now you're not doing you're not doing unrepeatable reads. And then uncommitted read or read uncommitted is no protections. Yes.
So is the snapshot isolation one of these levels?
So the question is snapshot isolation one of these levels? Snapshot isolation is a weird one. It's almost orthogonal to, so the answer is no, it's not in that main hierarchy. If you take the advanced class, we'll discuss this a bit further. But basically in 1992, when they came up with the ANSI standard for these isolation levels, the guy that was supposed to double check the other guy didn't double check that they missed snapshot isolation. So there's an anomaly that can occur under snapshot isolation that cannot occur in the other ones, but the ANSI standard doesn't support it. You don't have to worry about that. Just go with the ANSI standard. So serializable, repeatable read, read committed, uncommitted reads, read uncommitted. Yeah, snapshot isolation it's not a straight hierarchy. The tree is actually way more complicated, but we'll cover that in the advanced class if you take that. The ANSI ones are fine for the final exam. All right, so we talked about crash recovery. We talked about the different buffer pool policies, steal versus no steal. What does steal mean? Yes?
You can directly write over what an uncommitted transaction.
So she said, so with the steal policy means that the data system is allowed to write dirty records or dirty pages out the disk from an uncommitted transaction. Under no steal, you're not allowed to do that. And then force versus no force, somebody other than Paulina?
You have to write committed in that.
Correct. So she said you have to write all the dirty records out the disk before a transaction is allowed to be stated that it's committed. And then under no force, you don't have to do that. So with write-ahead logging, is it using steal versus no steal? It's using no steal. No, sorry, it's using steal. Wrong, right? Because with write-ahead logging, I'd have to make sure that the log records that correspond to the changes to the data pages, the log records have to be written to disk before my transaction is allowed to commit. But I'm allowed to, at some later point, write out the dirty records, after the transaction is already committed, which means that it's also no force. We talked about different logging schemes. The main distinction I care about is logical versus physical. Right? Physical is where you're actually writing out the low-level bits or bytes that got changed to the database system in your log records. And in logical logging, you're just writing a high-level command that made the change, so like the SQL query. And so there's trade-offs for these things, right? So if my query is going to update 1 billion tuples, with logical logging, all I have to have is that update query in a single log record, and that's enough information for me to record what change got made. Under physical logging, I have to have 1 billion log records that correspond to all the change I made to every single tuple. Then we talked about how to do checkpoints. So you should know about the difference between the fuzzy versus non-fuzzy, right? Fuzzy means that I'm allowed to write out inconsistent data to the database system or to the disk when I'm taking the checkpoint, but I need to know what was going on at the time in my system when I'm taking the checkpoint, so that I can reconcile during recovery what pages may or may not have gotten written during the checkpoint or may have been modified while I was taking the checkpoint. Right? In the non-fuzzy checkpoint case, you're basically stopping the world for a brief period while you write everything out. So that way you're guaranteed to have a consistent checkpoint. And then we talked about how to do areas of recovery for a lecture, right? What are the 3 phases? Right? The analyze, the redo, and the undo. So you should know how far back in the log you need to look at for each of those phases potentially. Right? You should know about the compensation log records. When do you write them? When do you read them? Right? If I have a compensation log record in my log and I apply it, but then I crash before I finish my recovery, when I come back around the second time, do I need to make another CLR for that first one? No, right? Because you've already done it. And the CLR has every information to tell you how to undo the original update. All right, and then we briefly talked about distributed databases. We can't obviously go real deep into this beyond what was covered in homework 5. So you know about the different system architectures we talked about: shared everything, shared disk, shared memory, shared nothing. What are the trade-offs for these? When would one be better than another? How are we actually going to do replication in these different environments, a distributed environment? How do we make sure that the database system is fault tolerant? How do we make sure that database system, if we're making updates, is consistent across all the copies of the data? How do we do partitioning? Again, high-level things. We talked about hash partitioning. What are the benefits of them? How to actually find the data you need? And then two-phase commit. Under what circumstances, and what steps would you do at different phases of the protocol? Don't worry about Paxos. That's too hard for a final exam in databases. Okay? So any questions about the final? To sweeten the deal, I forgot to announce this earlier. If you take the final exam, when you turn it in, I will give you a bus tub sticker. You can put it on your laptop. Okay? We have enough for everyone. Yes?
What is the duration of the exam?
This question is, what is the duration of the exam? It will be the same as the midterm, but you have 3 hours. And there's always somebody who takes 3 hours. Yeah. Yes. Rough. Yes.
Is there going to be a practice exam that's up?
Yes. His question is, will there be a practice exam? Yes. When I post the review guide, I will post the same way I did in the midterm. I'll post the practice exam. Yes.
Will it be multiple choice again?
His question is, will it be multiple choice? Yes. It's easier to grade. Yes.
So going back one slide, why do we make the distinction between force and steel? Like, can there ever be a case where you have no force, no steel, or steel and force?
All right, so his question is, I made the distinction between force versus no force, or steel versus no steel. Would there be a case where you would have one, like, when would you want to use one?
Like both or neither in that context.
So, no, I think you have to be sort of like steel no force or no steel force, right? We talked about shadow paging. Shadow paging was an example of no steel force, because I wasn't allowed to overwrite dirty pages from uncommitted transactions because I had this shadow copy on the side. I was making all my updates there, right? So that's the no steel part. And then the force part is when my transaction went to co-commit with shadow paging, I had to make sure all those dirty pages were flushed to disk, and then I flipped the root pointer to now point to the shadow becomes the new master. When I do that, I have to make sure everything's already flushed. So again, write-ahead logging is steel no force. Shadow paging is no steel force. And then the main takeaway was the write-ahead logging is almost always, I can't think of maybe there's some cases I haven't thought of. It's almost always better. And it's what every system uses. Most systems. Any other questions? Yes?
Unlike the midterm, we don't need a calculator for this.
Yes. So his question is, unlike the midterm, do I not need a calculator? I forgot to highlight that. Yes, you do not. You don't need it. Right? Again, think of what we did in the homeworks. We didn't estimate joins. We didn't. I don't think it's like. Whatever is that? There will be no questions on like query optimization stuff. That's the only thing I can think of. You may need a calculator, right? So don't worry about that. Any other questions? Yes.
Are there more example problems about the
shared routines. You know which one I'm talking about?
Like two-phase locking stuff, or the hierarchy?
Yeah, the hierarchy, where you lock different levels of.
Yeah. So her question is, are there more questions about like multi-granularity locking? So in the textbook, all the odd problems, the solutions are online. I haven't looked at the newer version, but like there might be some questions in there you could look at. And then you do the odd ones, and you go to the DB, the links on the course website, like dbbook.com. They'll have the solutions to the odd problems. You can just follow those. I'll put a link on the final review webpage. Yes.
Can I bring a note from midterm?
So actually, can you bring notes from midterm? One sheet. One sheet. Copy whatever you need. Okay. All right. So this is this is probably one of the favorite lectures. Well, they're all good, but because you get to talk about more databases. All right. So again, I asked everyone in the class to vote on what systems they were most interested in learning about. So here's the tally from last year for the top 10: CockroachDB, Spanner, and MongoDB. And here's what we ended up with this year, which is very surprising. Scuba came out first, followed by Mongo, followed by Cockroach. And surprisingly, this is my, I think, fifth or sixth year teaching like this Potpourri thing. Spanner's always been in the top 3, right? And so the only thing I could think of why people didn't vote for this as much is because the name got changed to Cloud Spanner, right? And maybe people didn't think it was the same thing. So that's okay. But Scuba is a really interesting system, so we'll start with that first, okay? All right, so Facebook Scuba. And I also noticed that people vote for the ones that if it has the name of the company in front of it, like Amazon Aurora, Baidu Oceanbase, then people vote for those things more. So anyway, all right, Facebook Scuba. So what we're trying to do here in the system Potpourri is to show you that we can now look at real-world systems and start using the vernacular that we've discussed all through the entire semester to sort of start to understand what this thing is actually doing. Right? So now I can say this thing's, it's a shared nothing distributed system, and you know what that means. You know what the implications of that are. You know what the performance characteristics, the performance challenges you would have in a system like this. So Scuba is an internal database system that Facebook has been working on for several years now. It was first announced in VLDB in 2013, and they've been still working on it. It's not open source, right? It's only until actually very recently is there now some public information about the newer version. And it actually turns out because the guy that is actually leading the project is CMU database alum. Like he got his PhD here before I showed up, and he's now running that whole running the development of this data system. And then his boss is actually his boss is the mother of another CS student here in the CS department who actually worked on BustHub over the summer, right? So it's all one giant CMU family. All right, so Scuba is it's designed for having low latency queries and ingestion of internal metric data generated from Facebook's different services. Right? So this is not running an OLTP application. This is not running, it's not like a giant warehouse. Think of like every single time you click something on Facebook, right, on the website, that causes a bunch of functions to get invoked on the servers, and they can have their developers instrument those function calls to keep track of the performance metrics, right, throughout the entire stack. And then all that data then gets shoved over to Scuba. Now they can use that and then run queries on that data to try to figure out, why did this function run slower? What are some problems I'm seeing in my giant fleet? So the newer version of Scuba is now a column store. It's a distributed shared nothing system. It's using a tiered storage. This means that like you can have a in-memory cache, a flash cache, and then maybe slower disks below that. And then it's going to be using a heterogeneous hierarchical distributed architecture. And so one interesting thing about the system as well is that since they are trying to have this thing be really fast, right, you want to run your queries very quickly over a lot of data, they are not, although they're going to support SQL, they're not going to support joins, they're not going to support global sorting. So you can only write queries that access one single table, and you just have a where clause to do simple filtering, and then you can aggregations. Another interesting thing about it that's going to be different than everything we talked about before is that they're going to have replication to have redundant deployments of an entire Scuba cluster. So So you would think that, like, I have a bunch of machines, I send all my data to this cluster, but I'm also going to send it to two other clusters running in different data centers or different regions. But they're going to allow for lossy fault tolerance in this environment because the data that they're collecting, it's valuable, but not like bank account valuable, right? So like, say, you go click on something in your timeline on Facebook, that generates a bunch of performance metric data. If that data gets lost, right? It's not the end of the world. Obviously you don't want to lose everything, but they're going to tolerate queries to end up, maybe have false negatives or false positives because they're going to end up missing data that just end up getting missing. And so the way they're going to try to avoid that is by running multiple deployments. They'll run the query in different regions at the same time, and then when they get back the result, they see which query actually had the fewest number of missing data, and then they use that as the correct result. But if they lose some data, it's not a big deal. And actually, they're going to have a retention policy where you can say, any data stored in this table after 7 days, just throw it away. And who cares? All right. So here's the high-level pipeline of what they're trying to do. So you have your different application servers. Right? These are all running running the website, running all the back-end stuff you need to support the website. So these guys are going to be generating structured debug logs. So think of this as like a JSON document that the application server spits out to say, here's how much time I spent in the CPU for this function and that function. So then they're going to load this into this internal tool that they developed called Scribe. Think of this as sort of like a Kafka kind of thing where you have a bunch of log records coming in, and then you can have like a pub subsystem to say, here's how to categorize the data I've collected, and other systems get notified when new information arrives to it. So this is an older thing that's since over 10 years old. There's an open source version that they have on GitHub, but that was like abandoned a decade ago. So supposedly the internal version is much better than what's online now. All right. So the Scribe is now going to take the structured logs, look at some tag to say, it's generated for, this particular application type or this service, and it's going to combine them and get together based on that category. And then it's going to send them to this streaming platform, or they call it the tailer service, because they're just tailing the log. And this is just going to batch together a bunch of these log records they've gotten from Scribe. And then when they have a large enough batch, they're going to convert that into a columnar data file. Think of like Parquet or Orc that we talked about last week. Right? Just think of like a standalone file, almost like a CSV, but it's actually a binary column store. And so after they have a large enough batch, they're going to generate these column store files. And then now they're going to feed this into the leaf nodes in Scuba. And so we'll talk about the between aggregation nodes and leaf nodes, but this is basically the storage nodes. Think of this as like the shared disk architecture, but you can actually have run queries down here. Or the last class when Shashank talked about Oracle Exadata, right? They had the storage nodes at the bottom could actually do filtering and predicate evaluation down there. Same idea here. So now one additional thing they're going to do is that each of these leaf nodes are going to update this validation service with information about the number of tuples that they've inserted for each table. And we'll see in a second, this is how they're going to determine which when they run the query on multiple deployments or multiple clusters, they'll check that thing to say, well, how much data is actually missing? So I know I inserted 1 million tuples, but I only read maybe 500,000, so half of my data went missing. Again, they're not going to go freak out. That's okay in their environment, but they keep track of this and they know that which query is producing the most accurate result. So now it's a SQL system. So they have this SQL interface or these dashboards that people can use internally at Facebook that sends SQL queries to this execution layer, which then is going to send it to these aggregators, who then are going to farm it down to these leaf nodes. So I'll discuss this hierarchy in a few more slides. But this is an important distinction between other distributed databases we talked about because it's a heterogeneous environment. So the leaf nodes are doing things that are separate or different than what the aggregator nodes are doing. Right? And you obviously would have more of these because you have more data. Yes?
Category the same as attribute?
The question is, the category the same as attribute? Yes. Think of like, it's some internal tag that Facebook is ascribing to a particular class of log records. Right? So again, say it's like, I don't know, the Facebook inbox or Messenger, right? So you'd say that would be one category. So all the log records from the Messenger app get combined together. Okay. So again, all right, it's a heterogeneous architecture, and we're going to have leaf nodes and aggregator nodes. So the leaf nodes are going to store the columnar data that we're getting out from the record batchers in columnar format. And for each query, every query is going to go to every single leaf node. So there may not be data that the query needs on that leaf node, but they're not going to store any additional metadata or maintain any indexes on these leaf nodes to be able to figure out whether I need to touch data at them. So they're trying to make this thing be as fast as possible. They're trying to make this both in terms of how fast the query can execute, but also how fast you can ingest new data. So if I don't have to maintain any metadata or catalog information about which data is at what leaf node, then I can ingest new data very quickly. And then every query shows up and just scans everything. And then that determines whether you have data that you actually need. Does that make sense? Right? So like when we talked about partitioning before, we talked about how there's, and we'll see this in Mongo and Cockroach, they're going to maintain this state table that says, if you want data within this range or this hash value, go to these nodes. They're not going to have any of that. They just blast everything to every query goes everywhere. So the aggregator nodes, when they get a query, they're going to dispatch plan fragments to its children leaf nodes. They're then going to do, on the leaf nodes, they're going to do the scan and some basic computation, but then they're going to send the result up to the aggregator nodes, who are then going to combine the results from multiple leaf nodes to produce a single result, and then send that up to a root node who combines the final result. So this is going to allow them to be able to scale out the system very easily, because I now, if my aggregators are running slow, I can add those nodes because they don't have any state, right? That's not where the data is actually stored. Or if I need to scale out my leaf nodes, I just add more of those and keep my aggregator nodes the same. Right? It's a very interesting architecture that shows up in a lot of other Facebook system design. The MEMSQL guys, before they started MEMSQL, they spent some time at Facebook and they saw this kind of architecture, and then they sort of copied it or were inspired by it when they went off and built MEMSQL. So MEMSQL works the same way. Okay, so again, we talked about this tolerating lost data or missing data. So if a leaf node either has no data or that it's down and it can't produce any results within a timeout, then they just ignore it, and that's okay. And they use the validation service to figure out, well, how much data did this thing actually have, and that'll determine the quality of the query result. So let's see what the full pipeline looks like. So again, this is be considered one Scuba cluster. They're gonna have multiple instances of the same kind of cluster running in different data centers, different regions. And they're going to invoke a query on all of them at the same time. And they all get back the same result, and you pick out which one is the best one. So my query shows up. I want to do an aggregation of the number of events that crashed there was a crash on a Monday. Again, so I can only do single table queries. I can do aggregations. I can do group bys. I can do filters. I can do scans. But I can't do global sorting, and I can't do joins. So the root's going to get the query, and then it's going to break it up into query plan fragments that's going to then distribute down to the aggregators, and the aggregators are going to distribute them down to their leaf nodes. All the leaf nodes are now going to do a scan and then send results back up. But let's say while we're executing this query, this node goes down, which happens, right, if you have a large cluster. So everybody else can still run. Everybody else is still going to be able to do the computation for this query. And then they send the results back up to the aggregators, who then just, again, combine it together, right? So I'm doing a count. So I want to know the number of events that occurred. So this guy says I have 10 events. He has 20 events. So this guy just takes 10 plus 20 and produces 30, and then sends it up to the root. And the root does the same thing. It just adds all the results from different aggregators, and then produces the final result. So is this clear? Yes?
So does breaking up the query mean like sending the same query to each other? Because you can write anywhere, so it couldn't use any information to optimize, per se.
Say it again.
For example, if the query was to scan everything,
yes.
And then what does the root send to each of the aggregators?
All right, so this query is to scan everything, right? So there's no metadata, there's no catalog to tell me anything about whether or not these leaf nodes have the data that I have in my where clause.
Right.
So I don't know where type is, I don't know where time is. So I send it to everyone. So everyone essentially is going to, in this example here, everyone's going to do the exact same query on the leaf nodes. All right. So he's doing a count star where type equals crash, time equals Monday. He has 10. He just shoves that up. And this guy knows, well, I'm doing this count thing, so I need to add sum up the numbers together, produce the result.
Yeah. So you previously mentioned that we don't keep any metadata.
Yes.
Right. So then, is it true that for any query, the root always copies the same query to each of them?
This question is it true that for every single query, you would always copy the same query down to the leaf nodes? No, because like for averages, the way you do that is a count and a sum, and then you compute the average at the top. So that would be different. Yeah. So there really isn't any, since there's no joins, there's not really a query optimizer here. It's just I need to know what I just convert the SQL to a query plan and just shove that down. And there's some basic heuristics they probably do to figure out like how to actually break it up and send it down leaf nodes. Yes.
Why was the decision made to have both like a root and an aggregator as opposed to like a client just connect to a random aggregator and an aggregator aggregate across all the leaf nodes or something like that?
So his question is why was it decided to have a root node here and have all the clients go to this versus having everyone potentially go to any aggregator and then any aggregator can talk to anybody else? So my understanding is that there's actually a layer above this as well, the root, where they're doing a mission control. So they can do some things like, oh, if a node is sending too many queries, if a client's sending too many queries, maybe we want to throttle them. Or like if I know I'm getting bad data from some set of these nodes, then I can have someone make a decision about what to exclude or not include in my query execution. So it allows them to have a single location to have a global view of what's going on in the cluster. It doesn't know about what's in the database, right? Because that would be too expensive to maintain and keep fresh all the time. It just knows that like these nodes are performing well or not well. Yes.
In this case, I produced 90, but if there were events in that leaf node, my result is not correct. So shouldn't I abort instead?
So his question is, say that this node had a ton of results, that would match my predicate. Wouldn't it be better for me to just abort this query because my count's gonna be way off? How do you know that this node has a lot of data that matters for your query?
I don't know.
You don't know. Yeah.
But in that case,
so again, so think about what this is designed for. This is designed for logs being generated by machines, right? It's not like, hey, here's my bank account. I want that to be, to the penny. So if you get loosey-goosey results, that still is probably okay. And then the way to sort of overcome that, again, is by having that validation service, they can determine how much data did they actually not read. So then also, again, then they have a bunch of redundant copies of the system running at the same time. They're all going to produce the same query. So the likelihood that every single cluster that's running Scuba for a single query is going to have this node fail exactly this node has this data fail is pretty low. So at least one of those clusters will have a more accurate result, and that's the one they'll use. And that's way different than what we've talked about the entire semester. That's why I like the system, because it's like we talked about never losing data. Now I'm saying it's okay to lose data. Because, again, it's like if the tree falls in the woods and no one's around to hear it, who cares? If this node goes down and no one knows and cares about what data is actually on it, it doesn't matter. And because they're not running Raft or Paxos every single time they're updating data, this thing can run really fast. All right, so this just summarizes what I've already said before, right? So for every Scuba deployment, there's going to be multiple Scuba deployments running in different regions. We're going to run the query at the same time on all the regions, and then they come back with the result, and then the result is annotated with information from the validation service that says how much data did I end up not reading, right? And you pick the one that read the most data. Okay. Again, so we know the guy Stavros that runs this. He got his PhD from CMU in 2007, 2008, and now he's in charge of this. So, all right, any questions? All right, good stuff. All right, number 2 was Mongo. Mongo is always picked every year. So let me ask you guys. I ask this every year. Why did you guys pick Mongo? I assume you picked Facebook because some of you want to get jobs at Facebook. So you think if I go in the job interview, I can talk intelligently about Scuba. Same thing for Mongo. Do you want to work at Mongo or do you want to use Mongo? Some people have already done internships. Some people are going to do internships there. Yes?
This is much different than what we usually do.
He says it's much different than what we normally do. Okay. So I've known the MongoDB guys for a long time. One of the co-founders actually went to Brown before I did. We've known Elliot since like 2009 when he first started the system. He would come give talks at the CS department there all the time. And I actually was there in August. They have a new office building. They used to be right around the corner from Times Square, which is awful. They're still in Midtown, but they have a nice office building. So they're a big deal if you have the sign for your company outside the building, right? Above that says Warner Music Group. They have loads of money. Mongo's doing pretty well. It's all for their databases. So this is their lobby. The lobby's nice, looks familiar, right? Yeah. The view is amazing. So this is from the kitchen. I mean, it was a cloudy day. But the view is absolutely stellar. And again, all paid for by databases. It's amazing. All right, so what is Mongo? Mongo is a distributed document model database management system. So when I say document, think of JSON, like a JSON object. And in the MongoDB world, the language for what we talked about the entire semester is going to be slightly different. So again, instead of saying tuple, they say document. Instead of saying table or relation, they say collection. But the high-level concepts are still the same. So it's one of the earliest or original NoSQL systems. It was open source. It used to be GPL, but now they switched to the server-side public license, and this is basically to protect them from Amazon. Right? MongoDB got so popular, they were worried about Amazon coming along and just running MongoDB in a hosted environment and selling it for cheaper than what MongoDB could. So they switched their license. Now, Amazon did come out with a system that does clone the MongoDB protocol called DocumentDB, but my understanding of how it works is that underneath the covers it's just Postgres. So the wire protocol looks and smells like looks like MongoDB, but underneath it is just Postgres. So it's going to be doing a centralized shared nothing architecture with a heterogeneous configuration. And originally, as this NoSQL system, they didn't do transactions, and they didn't do joins, they didn't do SQL. So right now, in the latest versions of Mongo, though they do transactions, they brought in transactions, and they also do joins. The only thing they haven't brought in is SQL. Now, there are some hacky tools that can convert SQL into MongoDB queries. As far as I know, I have never run across anybody that runs this and those things in production, right? So MongoDB is going to have their own API, which I'll show in a second. That is basically, you write JSON queries to read JSON data. So one important concept about the document data model, which is completely different that we talked about in the entire semester, is this concept of denormalization. So in the relational model, we would define our tables or define our relations, and we would use foreign keys to say there's a reference from this table to another table, right? So if I'm modeling Amazon, is my store information. So I have customers have orders, and orders have order items. So in a relational database system, I would define these as separate relations. And then if I want to say for a given customer, give me all the items that they bought, I would have to do a three-way join between these three tables. And the NoSQL guys argue that that was expensive to do these joins, because now you got to run your hash join and nested loop join, right? So what they would argue you'd want to do in a document data model is to denormalize, which basically says combine together the related information about a single entity in your application into a single JSON document, right? So instead of in this environment here, instead of having three different tables, you would have one table called customer, and then inside each customer record you would embed their orders, and then within each order you would embed their order items. So now if I want to go get all the order items that Andy bought, I go just get my customer record from the database system, and then I just traverse now inside the JSON document to get what I want. Now, MongoDB did not invent that idea. Right? That's an old idea from the 70s. XML databases did it in the early 2000s, late 1990s. The object-oriented guys did this in the 1980s. So MongoDB did not invent that. What MongoDB was sort of famous for was having a fast distributed JSON database system, right when sort of WebDrill and JavaScript was becoming prominent. So again, it would just look like this. In your JSON document would have inside of it an array called orders, and inside that you have additional JSON documents for every single order, and inside every single order you have an array for order items and then all the items that they bought. Right? So again, we've talked about this in actually the first class. From a performance standpoint, this is going to be really fast because again, it's one read to go get all Andy's order items. The bad thing is going to be, obviously, now we're going to duplicate a bunch of information about these different order items over and over again. And now I need to write my application code to make sure that everything I maintain the integrity of all of this information. So if I change the name of item, I have to write code to go through inside all my customer records to make sure I update everything. So the way you're going to execute queries is through a JSON-only query API. They don't have a query optimizer, at least not in a cost-based one that we talked about before. And I think I briefly talked about this when we talked about query optimization. So what they basically do is your query shows up, and they're going to generate sort of every possible combination for that given query. And then they're just going to blast every node with different combinations of that query. And then whatever one comes back first, then they learn that that's the better one to use because it came back more quickly. So the next time you execute that same query or similar query, they'll just reuse the query plan that they generated before. And they'll do this maybe like 1,000 times, and then just after the 1,000 query invocation, they'll do that sort of blast them all out first, or blast them all out and see which one comes back first thing. So you may think it's kind of hacky, right? I spent 2 lectures talking about how hard it is to do cost-based query optimization and how hard the problem actually would be. And they chose this because back in the day, they didn't do joins, so you didn't have to worry about join ordering. It basically was picking what index to use. So the random walk approach would actually work. I don't think they do anything sophisticated for the joins now. They might just use basic heuristic. This table or this collection is smaller than this one, so it's one's the inner versus the outer. They support JavaScript UDS. We actually didn't talk about UDS this semester. It's basically like a function you can write in your query that gets invoked on the database server side. They do now support joins, and they now support also multi-document transactions. So the early benchmark numbers for MongoDB were amazing. Like you could write data into it very quickly. Because what they were doing is, one, they weren't doing transactions, and they weren't actually guaranteeing anything was actually written to disk when you got response back that your write succeeded. It's actually even worse than that. If the database server got the packet for your write, they'd immediately come back with an acknowledgement and say, yeah, we got it. Then at some later point, the write would actually be executed and logged to disk. So if you wanted to see whether your write actually made it to disk, when you got back the response, you had to go back again and say, hey, did my write make it? Right? So you had to do 2 round trips to see whether your write was actually successful. That used to be the default for a long time. So if you look at the early benchmark numbers for MongoDB, they're amazing. Then 2013 or 2012, they actually turned that off. It's no longer the default. All right, now they're actually doing write-ahead log, and we'll talk about in a second. And they support multi-document transactions across multiple machines, which is impressive. It's not easy to do. All right, so the system architecture, I think we've already talked about before. It's a heterogeneous distributed components, shared nothing, with a centralized query router. They're doing master-slave replications. You can have your writes from one master node or master partition or shard will go off to other shards. So part of the reason I think MongoDB was very successful in the early days was they actually supported auto-sharding. So the idea was here that you just start shoving data into your database, and it'll be distributed across multiple nodes. But then if one of those nodes gets too full, MongoDB will automatically move your data around to balance things out. It didn't always work the way people thought it was going to work, but back in 2010, when I would go out to Silicon Valley and you ask people oh, they're doing a startup and they're basing it on MongoDB, you ask them why, and they would say, oh, because this auto-sharding thing was a big deal for them. Because at the very beginning, most people don't have much data because you're a startup, you have a stupid Twitter app, no one's using it, so you can run on a single machine. But of course, no one does a startup thinking that they're going to fail. Everyone thinks they're going to be big. So of course, I'm going to need 20 machines in the future. So I want to make sure MongoDB can scale up with me. Right? With MySQL and Postgres and other relational databases at the time, you couldn't do that. So I think this was a big deal. But there's a famous Foursquare outage. People know what Foursquare is. Think of how to describe this. It was an app you could check in what location you were in. It's still around, but it's not sort of it's not a phone app everyone uses. But they were using MongoDB, and there was a famous multi-day outage because the auto-sharding stuff got stuck. All right, so here's the architecture. Again, we talked about this before. And we have different node types. We have routers, we have config server, and we have shards. So every query from the application always goes to the router. And the router says, oh, I know I want to look up ID 101, but I don't know information about where that is. So I go to the config server. The config server tells me, and it looks in the shard table. It says, the data you want is located at this node. So then now the router knows how to send the query to the right location. Or it could blast it out to all of them. So again, this is an important distinction between the Scuba stuff and what we're talking about here. Scuba does not have this partition or sharding table. It blasts the query to everyone. In MongoDB, since you don't want to waste resources because you're trying to run update queries for your website real quickly, you maintain this information to figure out exactly where the query needs to go. So you're only touching the data. You're only touching a node that has the exact data you need. Yes?
Is there some sort of caching on the router?
Yeah. So the question is there caching on the router? Yes. So like you wouldn't always have to do this, but this would be this is considered to be stateless. So if I crash, I come back, I get my cache version from this again. But any update to like, if I say I'm doing the auto sharding stuff and I add a new node or I move some of the data to another thing, I update this thing and that's done as a transaction. Yes?
What's the origin of Mongo?
What is the origin of this? What do you mean?
Or like, if they got that from, if it has significance.
Oh, the naming?
Yeah.
Oh, I think Mongo just means humongous. That's all it is. Right? So this is like, actually the S, I don't know what that is, but like, maybe it's backwards? I don't know. No. Yeah, it's just daemon or data. It's probably just daemon. And Mongo S, I don't know what that means. I don't know what the S means. So, another thing I said during this semester was that never use mmap for your database. Well, when MongoDB first came out, they were using mmap for their database. And we actually did a little study on mmap database systems. And in our opinion, we haven't published this yet, the MongoDB implementation of using mmap is probably the most sophisticated one that we've ever seen. It's probably the best one, but it still sucks. It's still bad, right? So basically what happened is the way they would use mmap is they would have, they would basically maintain multiple copies of the database in memory, and you would do your updates to this like sort of private copy. That would then get read to disk, and then you had to replay the log to update the sort of the master copy. And so the OS could swap things out anytime it wanted. It was a big, big pain for them. The other big problem they had was they had a single lock for the database. Now this is not entirely because they were using mmap, but I think it's sort of probably helped make things easier using mmap. So that means that in the entire database system, even though you maybe split across multiple machines, in the early versions of MongoDB, you could only have one writer in the entire cluster at a time. So if I have 20 machines and I have one query that comes along, I basically lock all 20 machines to do update on one of them. And then in the newer versions of Mongo, since version 3, they got rid of this. So what they ended up doing was they bought this storage engine startup called WireTiger, which was founded by the guy that, one of the guys that invented BerkeleyDB. BerkeleyDB is an embedded database. WireTiger is an embedded database. We didn't really talk about this too much, but Postgres, MySQL, these are all database systems that like run as a standalone daemon or standalone system, and you have multiple clients connecting them. SQLite is typically used as an embedded database. You embed it inside your application, and it provides you the database functionality. But when your application closes, the database closes. So WireTiger is sort of like SQLite, but it doesn't support SQL. It supports like a key value store API. So probably one of the best acquisitions in a long time. They bought WireTiger and they replaced the mmap stuff with the WireTiger engine. So when you run MongoDB now, you get the WireTiger engine by default, and it's amazing. Question? Sorry. Yes.
Why, if using mmap is so complex, why would they use it?
This question is, if using mmap is so complex, why would you use this? So again, I want to prove this scientifically. I can't yet, so just take everything what I say, like this is my opinion. Mmap is like a seductress, right? It's like, it's this sexy thing that looks like gives you what you want for a buffer pool manager, right, without having to do it, because the OS does it for you. You don't need an eviction policy. The OS does that. You don't need to worry about paging, keeping track of dirty pages and things like that. The OS does that. So it's this thing that looks like it's going to give you everything you want, but it's like, it's the extra 5% you actually need to actually make it be durable and safe. That's when all the problems come in. So sort of like the query optimizer. Instead of building query optimizer, let's do something really simple and just blast everything out and see what comes back first. So instead of building a buffer pool manager, I'll just use the OS's buffer pool cache, or the mmap cache.
Did they not realize that when they started?
Let's take that one offline. Elliot's a really smart guy, the co-founder. and wildly successful, right? Like, it's a public company, right? I think, by using mmap, although it causes problems in, it can cause problems when you really start to try to scale and hammer the system, it allows you to build a system pretty quickly. So instead of spending 6 months having to develop a buffer manager that's safe and transactional and things like that, just use these OS mmap. And then when they got enough customers, they got enough money, they bought WireTiger and did it right. MySQL was the same way, right? Well, it didn't use mmap, at least I don't think. Like MySQL with InnoDB is amazing. InnoDB is fantastic. It's a solid database engine, storage engine. But the original engine they used was MyISAM. That thing sucked. That thing lost data all the time, right? You have corruption. And so, but it got MySQL up and running pretty quickly. A lot of people were using it, and then eventually InnoDB came along and MySQL bought them out and started using it. It's not a very uncommon strategy for a database business. All right, let's do a demo. So what I'm going to have to tell you is semi-illegal. All right, any questions about Mongo? Yes?
Why might you want to use Mongo over other?
This question is, why would you want to maybe use Mongo over others? So I think that being a distributed architecture matters a lot. The document model is actually better for application development, right? Think about it. When you write Python code, you write Java code, you're writing in objects. These are object-oriented programming languages. And so it kind of, if you can have now your object just be written out as a JSON document and then put into the database and fetch it back in and reinstantiate it in your application code, that could potentially be faster. But the thing I would stress, though, there's nothing about what MongoDB is doing because it's a document database system that is different than anything we talked about this entire semester. WireTiger doesn't know that it's actually being used for a document database system. It's doing write-ahead logging. It's doing all the crash recovery stuff we're doing. It's doing transactions underneath the covers in the same way that we talked about. So there's nothing about it in the document model that invalidates or changes anything we talked about here today. It's all at the application level, right? It's all sort of at the client level, what the query looks like, what the query is actually going to do. Everything else below is everything we talked about the entire semester. Yes?
Do they use some special compression techniques?
The question is, do they use special compression techniques? So that would be in WireTiger. I think it's just snappy. Yeah. Yes?
So does that mean that if I use MongoDB, anyone can access my data?
Again, the older versions, the default username and password is test. It's not that way anymore. Yes. Okay. All right. So the last one we have 10 minutes left is CockroachDB. Actually, I was there in the summer as well. So when I went, MongoDB and CockroachDB, their headquarters are in New York City. So when I was out visiting Cockroach or whatever, I visited both of them at the same time. Right, this is their old office. They had this nice little pixel art thing for the Cockroach. I was actually, this is their newer office though. I was actually surprised how big it actually is. I gave a talk there. They just raised $55 million, the Series C round, which is a lot of money for a database company. So that's actually very impressive. I assume that means they're doing well. So that's good. All right, so CockroachDB started in 2015 by some ex-Google employees. They were, I think, incorrectly characterized as the open source version of Spanner from Google Spanner. I don't think they ever said that, but people sort of attributed that to them. I would not say that's true at all. CockroachDB is sort of the core architecture is fundamentally different than Spanner, and Spanner has one magic piece that nobody else has, that Cockroach doesn't do, and nobody else does. So it is a decentralized, shared nothing, homogeneous database system architecture, and they're going to be doing range partitioning. The internal storage engine that they're going to use is RocksDB. So the same question is, why would anyone want to use mmap, right? Well, my answer was because you don't have to build that piece yourself. So CockroachDB, they didn't want to spend time writing a storage manager, right? The same way that, the WireTiger piece from MongoDB. So a lot of these newer database system startups, they're using RocksDB or LevelDB, these embedded storage engines, so they don't have to worry about reading, writing data from disk, and they worry about the higher level parts of managing transactions in a distributed environment. So they're going to be doing multi-version concurrency control with optimistic concurrency control protocol. And I don't know if this is still true, but they're only going to support serializable snapshot isolation. So I don't think they support the other isolation levels. They also speak the Postgres wire protocol. So that means that if you have an existing Postgres application, you can just, in theory, point it to CockroachDB. If it's pointing at Postgres now, you migrate your data over to CockroachDB, and you don't have to change potentially any of the SQL. It's not entirely true for everything. Like there's some things that are different, like auto increment keys. But in general, migrating to CockroachDB from Postgres should not be an onerous thing. So at its core, CockroachDB is a distributed key value store, a transactional distributed key value store. So that means that the lower storage engine of the system, at RocksDB is a key value system, but then the way they're doing transactions, or sorry, the way they're managing the database across multiple machines is essentially just going to be a key value store. And so using that, now they can build layers above that to provide the full sort of SQL compatibility that you would want. Right? So once you get past, like the SQL query shows up, they can then convert that SQL query. The query plan is essentially going to be a bunch of key value API calls that can then read and write data from different nodes. So the way they're going to coordinate the updates throughout the system is using Raft. Raft is essentially, at a high level, the same thing as Paxos. Right? It's a consensus protocol that allows me to say, when I make an update and I want to commit a transaction across multiple machines, everyone's going to agree, or quorum has to agree that the update's allowed to proceed or to occur in order for that transaction to be able to commit. So the way they're going to do OCC is through using timestamps, is using what are called hybrid clocks. So I think I talked about this a little bit, or Prashant talked about this when we talked about timestamp concurrency control. We need a way to have a clock that we can uniquely identify every transaction, and that clock needs to always be increasing. So we know what transaction in the serializable order as during the execution, what transaction came before the other. So you could just use the physical clock, which is from the actual CPU, like the machine itself, what's the system time. But the problem with that one is that's not going to be guaranteed to be highly synchronized across multiple machines. Right? There's every computer has a clock. That clock is not super accurate. It's not like an atomic clock, right? That's going to be counting electrons coming off an atom. It's going to be some kind of quartz crystal thing that has to approximate. So now you're going to have a bunch of skew in your clocks. And so now what could happen is, transaction arrives on one node, it thinks it's timestamp 1. Another transaction arrives on another node, it thinks it's timestamp 1. And now I have a conflict, or I have a conflict that I have to resolve. So the way they're going to handle that is through a hybrid clock, where you'll still use the system clock to try to get what the current time is, but then you'll also use a logical clock that allows you to have globally ordered transactions without having to synchronize every single time. So basically, it's like a little counter that says, here's my current timestamp, and my machine would add 1 to this logical counter to increase it. So what's going to happen is, again, under OCC, a transaction is going to stage all its writes in the system. So these are the modifications I want to make. Yes, question.
How is the hybrid clock different from the Google Spanner?
His question is, how is the hybrid clock different than the Google Spanner clock? The Google Spanner clock is not the Google Spanner. So the true. I don't want to get too much into Spanner. Google Spanner is relying on the hardware clocks to have super accurate times that are synchronized across all the machines. And the TrueTime API gives you a bound of how long you have to wait for someone to show up with a lower timestamp. It's a way to. It's basically this is like TrueTime, but using only software. So if you have really bad clock drift, like this one machine is 1 hour behind another machine, no transaction could potentially ever complete because every transaction thing that they're going to in the past and the future is going to get messed up. So you have to make sure that you try to keep your clocks in sync using like NTP. Spanner doesn't do that. Spanner does the GPS satellites plus the atomic clocks. They have super fine granularity. All right, so again, different than Scuba, all the metadata about where the data exists, what the transaction state is, that's going to exist in our own key value store as well. And that's all considered as transactional. So let's look at a simple example here. So we have our application comes along, and we want maybe update data in this cluster. So again, different from Scuba, we maintain a partition table just like a MongoDB to keep track of what node is responsible for what range of data. So when my query shows up, the first thing I have to consult is this partition table, which actually would be replicated on every single machine, and say, well, I want to access key or ID equals 50. What node is the leader for that? And then in this case here, it's this guy. So now my write has to go to here to do my update, and then the update has to get propagated to the other nodes, and then we use Raft to get everyone to agree that we're going to go ahead and commit this transaction. Right? So instead of using two-phase commit, they're just using Raft. So now if I want to do now a read, say for this ID equals 150, well, I'm always going to go to the leader where this guy's located, even though I have multiple copies of the data on different nodes. And in theory, I could read at these other nodes. But I always want to do my read on the leader to make sure that I'm reading the most consistent or up-to-date version of it. Because maybe these other nodes have not seen the latest update yet. Because in a Raft, you only need a quorum. You don't need to have every node agree, which is different. Two-phase commit, you need everyone. This one, you always need a quorum. So some node could be behind, but you're still allowed to commit a transaction. So to handle that, all the reads are always going to go to whatever the leader node is for an ID. And to avoid having every read query go to just to one node, that's why we have this table up here to tell us which one's the leader, and we're going to distribute that across multiple nodes, so the reads can then be scattered across multiple machines. Again, it's just doing the consensus protocol, the replicated writes that we talked about in the semester. So the core concepts aren't mind-blowing, aren't dramatically different than what we've already talked about. The hard part is the engineering, making this actually work. And that's what that's what they're spending all their time to make happen, so that you don't have lost writes or missing updates and things like that. Okay. All right. So let's finish up. So hopefully I conveyed throughout the entire semester that I love databases. They're awesome. You're gonna hit them. You're gonna hit them throughout the rest of your life. And so what hopefully this course has provided for you is the ability to say, something's running slow in our application because it's the database. Well, what kind of database system am I running on? What does my data look like? What does my query look like? It allows you to now make an informed decision about how these systems work and whether you're choosing the right database system for your given application or workload environment, right? Because not everyone's going to go off and build a database system, but I guarantee you, no matter what you do, especially even if you don't stay in the tech field, you're going to come across databases. Like Excel is a database. Right? So if you're using Excel, you're using a database. So, and the other thing I would say also too that's super important is I would avoid premature optimizations in deciding what database system to use. Always start with something that is maybe just good enough for what you need right now, and don't worry about potentially scaling up to millions of users in the future. Right? That was sort of my MongoDB example. Everyone said, "Oh, my startup is going to be huge. I'm going to have 1 million customers. Of course, I want to distribute a database that can scale out." Well, no. In the very beginning, you probably can just use Postgres or MySQL on a single box, and that'll get you, maybe for the next 2 years, that'll be good enough. And maybe you buy some better hardware and scale up a little bit more as your demand increases. But don't worry about bringing in a distributed system, because that's going to bring more complexities that you maybe need right now. And you should focus on what makes your what you need for your application to succeed. So people often ask me, what database system should I start with if I'm building a new application? My answer is Postgres or MySQL. For 99% of the applications, that's going to be good enough. Because what will happen is, if your application does blow up and you do have a lot of customers, what are you going to have? Money. So now you can go pay me to come tell you how to scale out your database, right? Or one of my students, right? So avoid introducing new complexity by bringing in going overboard with a database system maybe you don't need. Like maybe starting with Amazon RDS would be a good choice, and then you just scale up and buy a bigger instance size as your data size grows or your need grows. Okay. All right. Any questions? Yes. Boom. Okay. All right. So, yes. So I did get my test results came back last week. Right. This is it. It's mine. There's no. Oh. So the probability that I am the father of my child is 99.9999998%. So there is a 0.0000002% chance that it's not mine. But at this point, I've accepted my fate, and it's definitely my kid. Okay? Yeah, no, it's... Yeah, no, yeah, it's mine. All right, guys. So I'll see you at the final exam on Monday, and then I'll have office hours on Friday. And then again, this is the last class with DJ Drop Table. So again, round of applause for him being with us entire semester. Okay? All right, guys. Take care. Good luck with the rest of your classes.
Oh yeah, coming through with my shallon crew. 2 cents for a case, give me St. Nas brew. In the midst of broken bottles and crushed up cans, met the cows in the jam, or I'll try. With St. Nas in my system, crack another, I'm blessed. Let's go get the next one and get over. The object is to stay sober, lay on the sofa. Better yet, down my shoulder. I'll be champ, stressed out, could never be son. Ricochet jelly, hit the deli for a cold one. Naturally blessed, yes. My rap is like a laser beam, the boys in the bushes. St. Nas fill a canteen. Crack the bottle up and St. Nas, sipping through gold. You don't realize the drinking ain't only to be drunk. You can't drive, keep my people alive. And if the thing don't know you from a can of paint,